Thanks for inviting me. Really appreciate the opportunity to chat to you about my work. This is my very first paper, so I'm pretty excited about it and really interested to see your impressions of the work, any potential applications you can think of, any open questions you think are interesting. And really, I'd like to understand a little bit more about your work and, how it might be something we can look at some things together potentially in the future. So I thought I'd just sort of start by giving you a little bit of background about myself, because I think apart from Minshu, I haven't actually met any of you guys personally. So my background's a little bit different to most people entering the field. So I thought I'd just sort of explain where I come from and what I'm doing here, I guess. So basically, I did science law at the University of Sydney. That was many years ago now. So I finished up there and I went into industry. So I was really using more of my legal skills for a long time. Started up a couple of businesses. One was in the immigration field, so helping people get visas for Australia. And then a little bit later, I started up a technology startup called Vshore. I ran them for quite a number of years and then thought, okay, maybe it's time to do something different. So I sold up my interest in those businesses, I went traveling for a couple of years. So you can see me down the bottom here. I'm in Patagonia there after selling my businesses and looking pretty happy because I don't have as many staff to manage and, worries. So I spent a bit of time just thinking about what I should do next. And, I really wanted to get back into the science side. And when I was studying originally, I did pure maths as my science major. So I really wanted to, see if I could do something which actually applies some of the pure maths that I learned, things like group theory, representation theory, things along those lines. And so, yeah, I found out about quantum computing and started reading Nielsen Chuang like everybody else and saw there that, this group theory stuff was something that people were actually using to potentially build computers that might even change the world and do things we can't do with classical computers. So seemed really cool. So I went and saw Stephen Bartlett. I got introduced to him and started chatting and seemed like a great guy. And I said to him, well, I'm not a physicist, so can I still go into quantum computing? He said, no worries. Let's see how we go. So I started my PhD back just at the beginning of the pandemic in 2020 and started working with him and Ben Brown, who's probably somebody you've come across in the quantum error correction field. And as I said, this is my first paper on the XP Stabiliser Formalism, which is something quite new and I think it's quite interesting. So I'll just give you an outline of what I'll talk about today. So I'll start off with just an overview of the formalism and what it all means. So I'll start pretty slowly. I'll talk about the Pauli Stabiliser Formalism to start with and just review that and think about what it is about that formalism that we really like. And if we're going to generalize it, what are the things we would like to replicate in a new formalism? And yeah, really do a bit of revision on that and have a think about what it is that we're achieving with that formalism. And then I'll just introduce you to what this new formalism is, just do a few definitions and give you an idea about the wider range of states we can represent in the new formalism. And then, and I do want to spend a little bit of time on this, I just want to maybe spend a little bit of time talking about the applications and open questions. And here's where it would be great to maybe get some of your feedback on what your impressions are and what might be some interesting things to look at. Maybe we could do some stuff together. So I'll spend a bit of time on that. And so that'll probably take up most of the talk. And then I might dive into some particular areas in a bit more detail. And this part I kind of call it a workshop, but it's not a very heavy thing. It's just explaining some of the implications of the new formalism and just in a bit more detail and in a couple of examples, explaining what we can do with the formalism that may be a bit different to what we could do with the Pauli Stabiliser formalism. And in particular, something I want to focus on in this talk is that the new formalism, aside from giving us a wider range of codes and states, it also lets us understand some of the Pauli codes a lot better, because one of the side effects of this formalism is we can better understand the logical operator structure of stabilizer codes. And I'll show you a couple of examples of that, and you'll see exactly what I mean, hopefully. Okay, well, let's start off with looking at the Pauli Stabiliser formalism. What is it, and what is it that we'd like to generalize if we're going to make a wider formalism? And the way I think about the Pauli Stabiliser formalism is that it just gives us a much more efficient way to represent states, quantum states. And that's important because a general quantum state, say on n qubits, takes a lot of information to represent. If you're going to represent a general quantum state on n qubits, you actually need 2 to the n complex variables to represent it. And that makes them a little bit hard to study because, you know, representing an exponential amount of data, you can only represent very small states on a small number of qubits. So instead of dealing with those 2 to the n complex variables, we define a stabilizer state in the Pauli Stabiliser formalism as being the simultaneous +1 eigenspace of n independent Pauli operators, which we call stabilizer generators. And those Pauli operators, we just think of those as elements of the group identity times I, the normal X operator and the Z operator, tensored up n times. And basically, if we think about operators that way, we can actually represent them as binary vectors of length 2 times n plus 1. And this is something I learned from Minshu in that UTS course for the SQA. And I've basically done a lot of generalization of that way of thinking about things because it does make a lot of sense. And so basically, instead of having 2 to the n complex variables to represent our states, by using this formalism, we can actually represent states a lot more efficiently. And in particular, we can represent states using a polynomial number of discrete variables, because each of those operators you can think of as a binary vector, and you only need n of them. So one thing we like about the Pauli Stabiliser formalism is there are a lot of operations we know we can do quite efficiently. And so basically what we do is we just use linear algebra, and we can actually do a lot of operations on these Pauli Stabiliser states and code spaces. So the first thing we can do is we can actually determine the code space given a set of operators. And what we end up there is a set of code words which span our code space. And the code space, just to remind you, is the +1 simultaneous eigenspace of the stabilizer generators. On top of that, we can actually find the logical X and logical Z operators. And that's important because that tells us which protected operations we can do on our code space in a fault-tolerant way by implementing a transversal operator. So that can be done efficiently. We can also simulate evolution of these states. In particular, we can simulate unitary evolution by Clifford operators by doing operations on the stabilizers and seeing how they change under conjugation by the Clifford operator. And that can be done efficiently. And we can also simulate measurement of any Pauli operator on the code space. And there's a paper by Aronson and Gottesman where they show exactly how to do that. And we can do that efficiently too. So basically, in a sense, everything that we want to do for a Pauli stabilizer state, we can do efficiently on a classical computer. And there's a theorem called the Gottesman-Knill theorem, which says that we can do all of these operations efficiently. And in that sense, the Pauli stabilizer formalism is classically simulable. So these are the kinds of operations, if we're going to generalize the Pauli stabilizer formalism, we'd want to do as many of these as we can. And a lot of the focus of the paper that's just come out is just to find algorithms which generalize this for the XP formalism. And so you might say to yourself, well, the Pauli stabilizer formalism looks really great. Why would we want to generalize that? It's so useful. We can do everything that we want to do. Why would we bother ever extending that? Because it's perfectly good in the first place. Well, the first thing that you need to realize about the Pauli stabilizer formalism is that the range of states you could represent is quite limited. And there's some quite interesting states that we would really want to represent and explore and study. that show interesting behavior. So in terms of that, I think of things like the twisted quantum double models, some of which show non-abelian anion structures. It'd be nice to have a stabilizer code representation of those states, for instance. The other thing about it is that there's a lot of no-go theorems which apply for the Pauli stabilizer formalism, where we know that we can't do things we'd like to do. And in terms of these no-go theorems, the ones that you normally think about are things like self-correcting quantum memories. We know that we can't make them out of Pauli stabilizer codes. And the final thing is that because we can do everything on a classical computer and simulate those states so completely, in some sense, we're not really capturing anything that's new or different, and we're not capturing anything that relates to the quantum advantage that we expect from quantum computers. I feel like we're kind of missing something. So these are the reasons which got me thinking, all right, let's see what we can do in terms of generalizing and seeing what else is out there. So that's where I came up with this idea for the XP stabilizer formalism. So it is a really similar concept to the Pauli stabilizer formalism, but instead of just X and Z operators in our stabilizer generators, we also allow arbitrary rotations along the Z-axis as well as X. So how we define the formalism is that we choose an integer, which we call the precision, or capital N, which is greater than or equal to 2. And we let our generators be a form from the group omega I, X, and P, where we define all of those things as follows. Well, omega is just a 2nth root of unity. And this P operator is just a diagonal operator, which represents a 1 over n rotation around the Z-axis. And for each different choice of n, we get a different formalism. So if you choose precision n equals 2, you get back the Pauli stabilizer formalism. And if you choose n equals 4, you get back the XS stabilizer formalism. And this is where the idea really started from, reading this paper by Nee and Van der Nest and Boyer-Schapper on the XS stabilizer formalism. So really, the XP formalism is really the natural extension of the idea in the XS stabilizer formalism paper. So we've extended the formalism. Which new states do we capture? Do we get a wider range of states, or we just get the same thing as the the Pauli stabilizer formalism? So this slide just shows you in the single qubit context what states we can represent within the XP formalism. So the first block sphere you see there is the famous diagram from the original magic state distillation paper by Bravi and Kitiev. And it basically represents which states we can represent within the Pauli stabilizer formalism on one qubit. And you can see that the states we can represent lie within that double pyramid structure on a square base within that block sphere. We can represent anything within that octahedron, and anything beyond that can't be represented in the Pauli stabilizer formalism. So that really tells you the limited range of states we can represent in the Pauli stabilizer formalism. So in the XS paper, they generalize the Pauli stabilizer formalism, and I call that a precision n equals 4 formalism. And so you have X operators and S operators, which are the square root of Z. And within that formalism, you can represent any state within that double pyramid structure on an octagon basis. So it's a wider range of states. And in particular, you can see a very interesting state there, which is the eigenstate of the TXT inverse operator, which is an XS operator and happens to be a magic state. So I guess what you see here is that magic states do arise as eigenstates of XS operators. And so if you keep increasing the precision n and think about all of the states you can represent within the XP formalism, you get the diagram on the right, which is basically two cones joined together. And we can represent any state within those two cones by choosing a appropriate value of n. And that gives you an idea about the range of states we can represent on the single qubit. So obviously that's a little bit wider than what we can do within the Pauli Stabiliser formalism. Now let's have a look at the same question, but now think about multi-qubit states. So one of the famous results from the Pauli Stabiliser formalism is that any state you can represent as a stabilizer state can be thought of as a graph state by applying local Clifford operations. So essentially everything is a graph state. You apply operations and you get something you can write as a stabilizer state. So what is a graph state? Well, basically you have a graph which has n vertices, and on those vertices you put your qubits. And then you initialize your state in the plus state, tensored up n times. And for each edge on the graph, you apply a control Z operator on the vertices, and that gives you your graph state. And by taking any stabilizer state that you can think of in the Pauli Stabiliser formalism, you can convert that across to a graph state. And that essentially defines what you can represent in terms of multi-qubit states in the Pauli Stabiliser formalism. Now let's have a think about the XP Stabiliser formalism, which you see on the right-hand side there. So what we can do there is we can show an equivalence between XP formalism states and what I'm calling weighted hypergraph states. So the setup is quite similar to the Pauli situation. We start with a graph with n vertices, and we put qubits on the vertices. We start in the plus tensored up n times state. And these graphs are hypergraph graphs because the edges can include one or more vertices. And you can see here, the shaded blue triangle here is an edge with 3 vertices. And this edge right here is a traditional 2-vertex edge. So they're hypergraph graphs, but they're also weighted because for each of the edges, we can specify a weight, say Q. So here for this shaded triangle, the weight is 1. And here for the edge, which is on 2 vertices, our weight is 3. And then instead of just applying a control Z, we can apply a controlled P to the Q operator on the edge. And
sorry, Mark. What do you mean by the weight?
Yeah, it's just an integer between 0 and n minus 1.
Okay. Oh, I see.
And and you can think of generalizing a controlled Z operator to a controlled P operator, but say a 3-vertex edge would have a control P operator on it.
Okay.
Yeah. Yep. And that in the paper we show pretty much gives you an equivalence of XP states with weighted hypergraph states up to a certain embedding, which you explain in the paper. And I don't want to get too much into it in this, but yeah, you can't quite get the same level of equivalence as you do with the Pauli Stabiliser formalism to graph states. But it does describe fairly completely which states you can make within the XP formalism. And so when I'm thinking about how does this compare to what people have been using traditionally, the way that I think of it is that the XP formalism is probably similar in terms of the level of generality to the Qudit Stabiliser formalism. Now, the Qudit Stabiliser formalism is where you choose a Qudit dimension D and a number of Qudits N, and your stabilizers are tensors of generalized Pauli X and Pauli Z operators on those Qudits. In the case of the XP formalism, you choose a precision N and a number of qubits little n, which is a similar sort of set of parameters to what you define for Qudit codes. And so for Qudit codes, there is an idea of generalizing a Hadamard operator, and we call that the quantum Fourier transform. But a really important difference between what people have been doing before is that in the context of XP codes, we don't have the idea of a Hadamard operator. And by that, I mean an operator that swaps X operators with the diagonal Z or P operator component by conjugation. There is no such thing within the XP formalism. And you can pretty much show that there's no operator that meets the requirements for that operation. In terms of commutators, that's another thing that's quite different. When you look at the Pauli Stabiliser formalism and the Qt formalism, whenever you calculate a group commutator, it always ends up just being phase times the identity. So in the Pauli Stabiliser formalism, that means that two operators either commute or they anti-commute. In the case of the XP formalism, things are a little bit different because the group commutator is not just phase times the identity, it can be just a general diagonal operator. And that has important implications in terms of representing things like non-abelian anion systems, because there you may end up with braids that are actually diagonal operators rather than just phase operators. In terms of whether our stabilizers commute, definitely the case in the Pauli Stabiliser formalism and the Qt Stabiliser formalism. Your stabilizers need to commute for you to define a code space. But that's not the case when it comes to XP codes. You don't always have commuting stabilizers, and I'll show an example of a code where that's the case. But they, of course, may commute up to a diagonal operator. Another big difference is that in the Qt formalism, once you have a code space, that uniquely defines the stabilizer group, which stabilizes that code space. But that's not the case when it comes to the XP formalism. And in fact, there may be a range of different stabilizer groups that have the same code space. And again, we'll see an example of that a bit later on in the talk. Code space dimension, also quite easy to predict in the Qt situation. But in the XP situation, it's a lot more complicated. The eigenspaces of these operators are quite a lot more complicated and difficult to determine than in the Qt and the Pauli Stabiliser situation. And finally, in terms of simulation of measurements of operators, we can do that efficiently in the Qt and the Pauli Stabiliser formalisms, but that is not in general possible for arbitrary XP operators. So we lose that element of the Gottesman-Knil theorem, which says that everything we want to do in terms of simulating measurements can be done within the formalism. And so that is a really big difference between the two formalisms. So that pretty much gives you the big picture view of what's possible and what's not within the new formalism. And just to describe what's in the paper, well, basically we set out the framework and we translate as many of these algorithms across as we can. So we show how to determine the code space, how to convert between the view of an XP stabilizer state and a weighted hypergraph state. We've got an algorithm for that. We determine the logical operator structure, and that's something I want to spend a bit of time talking about today, because the methods in this paper give us a much better understanding of the logical operator structure, even for the codes that we work with day to day, the Pauli Stabiliser codes. You can get a much better understanding of what operators are possible to do in terms of transversal operations on the code space. In terms of measurement, we do have an efficient way of updating the generators and giving the probabilities for measurement of diagonal Paulis, so strings of Z and I operators. But in general, we show that we can't do that. So what happens is either estimating the probabilities reverts to an NP complete problem, or we go outside the formalism when we make a measurement. So we're no longer within the formalism, we no longer have a state that can be represented as an XP code space. And so one of the things I wanted to do when I was starting this work is to make sure that I had plenty of examples, and in the paper there's heaps of examples. So it's not just an abstract thing, you have things you can play with. And as part of the paper, we've also published a package in Python where you can actually play with the codes in the examples, add your own favorite code, see what comes out as a result, and play around with it. And you've got the link to the GitHub there. So just to summarize where we ended up with the formalism. So in the paper, we just show that we can get a broader range of states. We show that we can represent certain topological phases with non-abelian anyons. That's a known result from the XS paper, but we kind of explain why that happens. We see that the codes that we get in the XP formalism give us more complex logical operator structures that don't arise in the Pauli Stabiliser formalism. We also show that the measurements are not simulable, so we don't have a Gottesman-Kneel style theorem in this that's obvious. And we also show that these algorithms get less and less efficient when we increase the precision. So, and also sometimes when we increase the number of qubits, things get a little slow as well. So that makes me think that we're capturing something that for small codes is simulable, but as we make the precision higher or we make the codes bigger, it stops being classically simulable. And that suggests to me that we're onto something in terms of capturing some aspects of quantum advantage. And that maybe some of these codes will be able to do things that we can't do on classical computers and might be interesting in terms of applications for quantum computers as well. So in terms of open questions, I think there are just so many. And really one of the things I loved about the XS paper is that it just had heaps of juicy open questions. And I wanted to pay that forward and really make sure that, you know, when I did this work, I left heaps of juicy open questions so that, you know, I didn't solve everything, but left plenty for others to look at and get interested in and, you know, take it away. So I'd say probably the biggest open question is around error correction. And the reason that that is more complicated is that I mentioned before that the operators don't necessarily commute the stabilizer generators. And so that means that we can't necessarily simultaneously measure all of our syndromes. And so error correction is a little bit more complicated than it would otherwise be, say, for the QDIT stabilizer formalism or the Pauli stabilizer formalism. And so I had an idea there, which was to generalize the method that they use for code word stabilized codes. And that was a really interesting paper to me because basically you can think of these codes, and they're quite general, as being translations of basically graph states. And when you have any sort of error, the errors migrate along the edges of those graphs and end up just being strings of Z operators. And I thought maybe this is the right way to look at error correction for these codes, because we know how to convert back and forth between XP stabilizer states and these weighted hypergraph states. And that in many ways, the structure of these codes is similar to these code word stabilized codes. So definitely haven't figured that out, but I think that that is a really important question to look at next. I also thought that magic state distillation could be a great application for these codes. And really the reason is based on the fact that, firstly, you can actually represent magic states as the +1 eigenspaces of these XP operators. But secondly, because the logical operator structure is so much more diverse and rich in this formalism, that when you're doing magic state distillation, you want to have codes which have logical operators which are non-Clifford operators. And when we look at the XP formalism, we see a lot of non-Clifford logical operators. They just really do arise naturally as part of the logical operator structure of the codes that we look at. And I'll show an example of these higher Clifford operator level operators as part of the examples in a minute. The next thing that I wanted to think about was, well, in the XS paper, they showed that these quantum twisted double models could be represented and that they gave rise to these non-abelian anyon models. So what I wanted to do is maybe have a look and see, you know, which of these topological phases we can represent in this new formalism. So one of my colleagues, Don Williamson, has got a paper which I reference here, where he shows that pretty much any of the abelian anyon models that we think of can be represented within the acute stabilizer formalism. And so I'd really pose a similar question and say, well, okay, within the XP formalism, which topological phases can we represent, and how many of those are non-abelian, and what can we actually do within this formalism? Definitely a nice, juicy, open question, that one. And so I mentioned the idea of self-correcting quantum memories before as possibly a no-go theorem that may not apply when it comes to the XP formalism. And I think one of the questions you probably want to look at is whether there's always a commuting parent Hamiltonian for XP codes. And I've referenced a paper there, which might be a good one to look at next if people are interested in that matter. But obviously a self-correcting quantum memory, it seems to be one of these ideal things we would love to have. And if XP codes are a natural way of implementing this, that'd be quite interesting. And the final one I have there is with our new understanding of the logical operator structure of codes, is there some way of using that to design codes which have a logical operator structure that we want? And really that's the dream, is, you know, let's look for non-Clifford operators for our magic state distillation. Let's figure out what the requirements are for those codes. Let's optimize them for distance and all that stuff so that we can do really good magic state distillation routines or other applications which need these higher level Clifford operators. And so that's really the open questions I think could be interesting, but I'd be really interested to hear your impressions at this point, sort of, you know, throw around a few ideas and see, you know, what you think might be interesting to look at in terms of this formalism. So yeah, if there are any questions or any, you know, thoughts that people have at this point, I'm happy to have a chat and sort of see what you guys think. But otherwise, I'm happy to jump into a bit more detail and jump into the workshop side of things. So are there any sort of thoughts or questions at this point? Not at this stage? All right, well, what I might do is I might jump into just looking at a bit more detail in terms of the formalism and how it works. So let me do that then. Okay, so the things that I wanted to maybe jump into and look at in a bit more detail. First of all, you know, how do these operators work in terms of the algebra? We understand the algebra of Pauli Stabiliser Formalism operators quite well. And really what we do there is we use this idea of a symplectic product to understand the commutation relationships between Pauli operators. And that really gives us the structure that we need to do algebra with our Pauli operators. And so in that section, I'm going to explain how that generalizes to the XP context. And hopefully you can see that that is actually quite a nice, elegant and efficient way to look at these operators. And we can do algebraic operations on them quite efficiently. And I also want to just explain, you know, how I think about these operators and a bit of notation so that for the next part, which is the logical operator structure, you can follow what I'm saying about the logical operators. So with the logical operator structure section, I think this is probably one of the immediate consequences of the paper, and probably the most important at this stage, is that we can actually understand the logical operator structure very completely using this formalism. And that applies even to Pauli codes. And I'm going to show you a couple of examples of Pauli codes and how we can use the formalism to really understand the logical operator structure and think about how to design codes which have our desired logical operator structure and how that might have some consequences. So in terms of the algebra of XP operators, what I do in the paper is I show how we can represent each of these operators as a vector. And that's similar to what we do in the Pauli Stabiliser formalism. So in this case, we just look at a representation which is a vector of integers. And we basically need 2n plus 1 integers to represent our operators. And the way that I represent these operators is that I split the vector into a phase component, which is this P here, an X component, which is of length N, and a Z component also of length N. And so this notation here tells me that I've got an XP operator of precision big N with phase component P, X component X, and Z component Z. So anything which is bold is a vector. So this is defined to be this particular operator, which is a phase component, omega to the P. Remember that omega is a 2nth root of unity. And then our X and Z components are calculated like this. It's just a tensor product. If xi is 1, we get an X component. Otherwise, we have no X component there. And the phase component is really explained in terms of these P operators on each of the qubits raised to whatever the Z component corresponding to that qubit is. And so we can actually find a unique vector representation. Instead of integers, we can think of the phase as being from integers modulo 2 big N. The X component is from integers modulo 2, and the Z component is integers modulo N, big N. And we can explain all of the algebraic operations really elegantly and efficiently in terms of adding these vectors together, multiplying them together, and using this special anti-symmetric operator, which I denote as this big D operator acting on a vector Z. So the big D basically is this XP operator. The phase is just you add together all the components of the Z vector, modulo 2n. There's no X component, so it's a diagonal operator, so that's a 0 vector. And we just invert the Z component, and it's minus Z there. So this anti-symmetric operator can then be used to give us all of our algebraic identities, and it's really quite nice. So for instance, multiplication of two XP operators just reduces to adding the vector representations and multiplying by an adjustment factor, which is given by this anti-symmetric operator here, which is 2 times x2, which is the X component of this operator, times the Z component of the first operator. And these are component-wise multiplications. So you can see that it's quite similar to the Pauli case, where when we multiply two Pauli operators, we add the vector representations and we just adjust the phase to either +1 or -1, depending on whether those operators commute or not. And in the XP case, it's similar, but this time this anti-symmetric operator may not only just involve a phase, but it may involve a diagonal component as well, a non-trivial diagonal component. So it's a nice generalization of what we do within the Pauli Stabiliser formalism. Once you have this basic multiplication rule, you can actually generalize that to get a rule for any arbitrary power over an operator. And you can also figure out what the group commutator is of two operators. And you can see these nice, elegant formulas, which are all based on this anti-symmetric operator, which we've introduced. This final one here just tells you how an XP operator acts on a computational basis element. So really, this is all you need to know about the algebra of XP operators. It's a very nice, simple, and very easy to implement on a computer using, as I've done here, NumPy. So just to give you an example of this, I'll just show you on this next couple of slides how to calculate a group commutator, which is basically this formula here. And that's a really fundamental algebraic operation that we'll see time and time again. So it's a good one to look at. So let's set our precision to be big N equals 4. So in this case, it's a 2nth root of unity. So that means our omega is 2 pi r on 8, which is basically the square root of I. So omega to the 8 will equal 1 because it's a 2n, so 8th root of unity. And our phase operator, our P, is the diagonal of 1 and omega squared, which is the diagonal of 1 and I, so that this is an S operator. When we raise that to the 4th power, we get back the identity. So this is really the excess formalism that's in the previous paper that I started from. So let's just do an example here of that commutator. So let's take our first operator to be x raised to the 4th power there, and a2 to be s tensored up 4 times. So the representation of those operators is like this. So x tensored 4 times, there's no phase component. Our x component is 1 for each of the qubits, and there's no z component. So p1 is 0, x1 is the 1s, and z1 is 0. And when we do the same thing for s tensored 4 times, we get this form of operator, no phase, no x component, and just an s operator on each of the qubits, which is what we expect. So when we calculate the group commutator, we use the formula from the previous table. And what we see is that because A2 has no x component, all of these terms disappear. Is x2 is 0, x2 is 0, x2 is 0. So this tells us that with a diagonal operator, our group commutators are always going to be of this form, 2x1, z2. So if we plug these numbers in, we get d4 of 2, 2, 2, 2. And the phase component will be the sum of that vector, which is 8. And the z component will be minus that, which modulo 4 is still all the 2s. So you can see here that our phase component is omega to the 8, and it's a 2nth root of unity. So this turns into a phase of 1. And s squared gives us a z operator. So you can see here an example of the group commutator of 2 operators not being a phase times the identity, but rather a diagonal operator. And that's the important difference between the formalisms that we've considered. And remember this example because we'll see it again. Okay, let's have a look at some examples of how we can look at Pauli Stabiliser codes within the XP formalism and get a better understanding of the logical operator structure. And I'll look at 2 here. First one is what I call hypercube codes. And the second one is Reed-Muller codes. And I'll show you how we can look at these as higher precision XP codes and understand the logical operator structure a lot better than using traditional methods. So first of all, let's have a look at what is the main thing you need to know about the logical operator structure of XP codes. And really the most important thing is that some of the things that we are used to in the Pauli Stabiliser formalism don't apply anymore. And I'll just highlight some of the main differences. So let's start off with a set of stabilizer generators, say G, and those will specify a code space. We take that set of operators and we figure out a set of canonical generators, which are denoted here Sx and Sz. So X are the non-diagonal ones and Z are the diagonal ones. And really you can think of that as an independent set of generators in standard form. So we get rid of all the redundant ones and we put everything in a nice standard form so that we can tell whether 2 groups are the same. It's a list of generators that is truly canonical that allows us to distinguish different groups of XP operators. So yeah, in that case, Sx and Sz generate the same group as G, and that's a construction which we talk about in the paper. But on top of that, we have what we call the logical identity group. And these are XP operators which fix each element of the code space. And this is a really important difference between the XP formalism and the ones that we've looked at before, in that the stabilizer group does not uniquely identify, well, the code space is not uniquely identify the stabilizer group. And in fact, the group generated by the stabilizer generators will always be a subgroup of the logical identity group, but it may not be equal to it. And in the case of the Reed-Muller codes, we'll show you an example of that. So what that also means is that many different stabilizer groups can have the same code space within the XP formalism. Okay, and on top of that, we have what we call the logical XP group. This is the XP operators that preserve the code space that might otherwise have a non-trivial action on the elements. And what we're going to try and do is to determine the generators for the logical identity group and the logical XP group, so the non-trivial ones. And in the paper, we show some algorithms for doing that. So when you apply this, what you actually do is you look at commutators between operators and elements of the logical identity group. And if a logical operator has all the group commutators with elements of the logical identity group are themselves in the logical identity group, then it is a logical operator and vice versa. And that's the test that we use for creating a list of generators for the logical operator group. So let's have a look at a couple of examples. And so the first one I have here is the hypercube idea, and that's from a blog post by Earl Campbell. And what we do there is we take a hypercube of dimension big D, and we have qubits on the vertices. And our stabilizer generators, well, we have one non-diagonal generator, which is where we have an X operator on each of the vertices of the hypercube. And then we have a series of diagonal stabilizer generators where we just put a Z operator on each of the vertices of each dimension D-1 face. And then we can find all the transversal logical operators of XP form by considering this an XP code of precision 2 to the D. So for D greater than 1, you can see that this is an XP code rather than a Pauli code. And what we find out is we can actually address any of the code words and apply a -1 phase. So we basically have logical control to the D-1Z operators, which are non-Clifford in general. So to give an example of that, let's take a dimension big D equals 3, which is a cube. In that case, we have 8 qubits, physical qubits, and we have a precision 8 code. So this is a bit different to what anyone else has looked at before. This is an XT code, basically. And our stabilizer generators look like this. This is a X operator on each of the vertices. So that's this operator here. And our diagonal ones, well, basically, it's a Z operator on each of the two-dimensional faces. So you can see here Z operators on each of the vertices of this two-dimensional face here, which might represent this. And we can also look at the face on the opposite side, which we get to by applying this operator. And if we multiply these two together, we get the Z operators on the opposite face. And the independent centers looks like this. And in fact, if you do a counting argument, you can show that you end up with 3 logical qubits. These are the non-diagonal logical operators, but where it gets really interesting is where we look at the diagonal operators. And all of the diagonal logical operators can be generated from this set of operators. And you can see that each of these applies a phase of -1 to a particular code word. So this is logical 000, logical 100, and these are the corresponding ways of representing those. And when we look at this geometrically, what we see is that the control Z operators have support on the entire hypercube. So they're really 3-dimensional operators. So here the blue 3s represent T to the 3, and the red 1s represent T operators. But we can also multiply these together and make control Z operators. And when we do that, we find that we get 2-dimensional operators. So here on the bottom face and here on the face facing us. And then we can multiply these two together and get logical Z operators. And you can see that these are now 1-dimensional operators. and that they anti-commute with our two-dimensional logical X operators. So just an example of how the formalism lets us better understanding of the logical operator structure of even Pauli Stabiliser formalism codes. So the second example I wanted to look at is Reed-Muller codes. And this is a really familiar example to a lot of you. It's one of the most widely used range of codes. And so what I'm really thinking about here is, all right, what are Reed-Muller codes really? And how can we generalize them in a nice way to produce useful codes that could be very good for the tasks we want to do in quantum computing? So let's just have a look at the 7-qubit Reed-Muller code. You can think of this as being 3 square faces meeting a common point. So you can see a blue square there, a green square there, and a red square there. And you can see that each pair of faces meets at an edge. So these two faces meeting this edge, and they all have a common point at the middle. And what we do is we put qubits on the vertices, and the stabilizer generators, we have 2 for each face. We have one with Z operators on each vertex, one with X operators on each vertex, and we have 3 sets of those. And the nice thing about that is we have a full set of transversal logical Clifford operators. So we've got Hadamard transversal, S transversal. And if we take 2 copies of that code, we also have a transversal control Z. So that is a very, very nice code. And the question I have is, can we then generalize this to find, say, an LDPC code, which has a better rate and a better distance, where we have the same logical operator structure, i.e., say, a controlled Z between any 2 pairs of logical qubits, or potentially a logical S on all of those qubits as well. That'd be a useful code to find. And I'm hoping to use these new techniques to be able to design codes with a desired logical operator structure like that. We can also play that same game in a higher dimension. Now, this time we're looking at the 15-qubit Reed-Muller code, and you can think of that as being 4 cubic faces meeting in a common point instead of squares. So you can see the red cube, the green cube, the yellow cube, and the red cube. They all meet in a square. So you can see the red and the blue actually meets in a square here. So 4 qubits in common. And we can actually define this in a different way to what we normally do for Reed-Muller codes. So you can actually think of this as a symmetric code where we look at each face, each cube, and apply S operators on each vertex, and another set where we have X operators on each vertex. And you might say, wow, that's different to how you normally define it, but it has the same code space as the normal Reed-Muller code, which is a Pauli code. But this is an illustration of the fact that there are 2 different codes that we have here with 2 different stabilizer groups, which actually have the same code space. Just an illustration of that within the XP formalism. Now let's have a think about what's the commutator between this red cube, if we have X's everywhere for that stabilizer, and this green cube, if we have S operators on each of the vertexes. You can see that these intersect on just this square here. And in fact, that it's the same question that we looked at before for the group commutator of S and X. So if you remember that example, we actually ended up with the commutator, which was the tensor of 4 Z operators together. And so you can see this is another example of a code where the stabilizer generators do not commute, but they commute up to a diagonal operator. So the interesting question I have about this one is that this code happens to have a transversal logical T operator, and we can keep playing that game. We can keep on increasing the dimension, creating a symmetric code by applying P operators and X operators to the same faces. And we effectively get a generalization of the idea of a color code into higher degrees of precision for our XP codes. And you can see that within the Reed-Muller family, this gives you logical P operators in general, up to whatever level of the Clifford hierarchy we would like to make. So the question I have is, how do we generalize that to LDPC codes, which say have a logical T operator, which could then be super useful for things like magic state distillation? So that's it for my talk today. Hopefully you found that interesting and useful. Happy to take questions at this stage, but yeah, if you have any thoughts or ideas, I'd be more than willing to hear about them and talk further. Thank you, guys.
Thank you. Thank you, Mark.
Thanks, guys.
I want to make a comment. So this is really a nice presentation. So very clear and it's on time. It's very, very nice.
Thanks heaps. Thanks heaps.
Yeah, yeah. And I wanna mention that in my class, Mark got the high score in that year. So
oh really?
yeah. You got the high score, and I still remember your presentation and your exercise sheet. It's very clear and nice.
Oh, thank you so much. I really appreciate it.
And I really I think the work is also very nice, very clear, and also with a lot of examples. So one of the questions that I have is that transversal logic operation is very important. So for example, in this case, you have a transversal logic T operators. Would you make it? So for example, this control operations, control NOTs, if you could you also have other transversal logic operators with your formalisms?
Yeah, I don't think I can make a controlled NOT. It doesn't seem to arise naturally. I get transversal control Zs and control phase. But one algorithm I'm looking at the moment, all of the operators you've seen so far are where we apply transversal operations on a single physical qubit. So the obvious generalization would be to next look at transversal operations on 2 qubits. So control phase on 2. And I think I've got an algorithm for that too.
Okay.
So yeah,
great.
That means you can then start looking at applying arbitrary Cliffords of any type that you want using low circuit depth methods. Okay. So that's the next bit of work I'm doing right now.
Great. I think that's the right directions, like fault tolerant computation with these formalisms. If you could somehow make it improve upon current stabilizer formalism, I think that would be nice.
Yeah. No, I'm pretty pumped up about it. Like I'm really interested in logical operations at the moment. But I'd really like to get to the point where I can design a code which has whatever logical operator structure I like. And
yeah. Oh, okay.
That's
quite ambitious goal.
That's right. But yeah, I mean, it's what we're in it for, you know. Quantum computing, it is an ambitious subject.
Okay, good. Okay.
All right, cool. Well, thank you very much. And unless there's other questions, I'll go on with the rest of my day. And thanks again for the opportunity.
Okay. Thank you.
Okay. Thanks, guys.
Thank you. Bye. Bye, Mark. So should we just use this do we just continue our group meeting from here?
Oh yeah, please.
Okay. Or do you need a 5 minutes break?
Yeah, it would be nice just to go.
Yeah. So maybe let's take a 5 minutes break so we could resume at 11:07.